Hello and welcome to our mid-session presentation for the Light Sensor project.
Hi, my name is Josh and I was responsible for implementing the light sensors of the project. A light sensor functions by measuring the radiant energy that exists in a very narrow range of frequencies, and which ranges from infrared light to visible up to the ultraviolet light spectrum. The design intent for the light sensor is to connect to the FPGA through serial peripheral interface and have a lookup table to convert the readings into lux. This would require calibration through testing, which we're going to use a phone as the basis and test different light levels from 0 through to 1000. Unfortunately, due to delays in shipping, the light sensor has yet to arrive, and instead of calibrating, our time was instead spent focusing on the memory module and implementing the button behaviors. The code used for the Arduino was copied from the information in Module 5 on Canvas. This means that for the time being, the Arduino is acting as a master, with the FPGA being the slave. This is okay for the time being, as the only other SPI device has yet to be implemented.
Two LCDs are used in this design, a 16x2 LCD and a colored SPI LCD. The 16x2 LCD, otherwise known as the character LCD, displays all record results and lists the calculated average value. Users are presented with an option to navigate the LCD screen using two mechanical buttons, one for left and one for right direction. Values are recorded and stored in memory by pressing the record button, and can be cleared by pressing the reset button. Individual recorded results can be deleted by selecting the desired result using the navigation buttons and pressing the reset button once. Holding the reset button clears all results from the memory and display. The colored LCD is intended to be used for a heat map. Light readings taken throughout the room will be marked on the 2D image of the room. To determine the position of each recorded value in the room, an ESP Wi-Fi module will be implemented. It scans for nearby Wi-Fi networks to calculate its position. However, one concern with using Wi-Fi positioning is the accuracy.
Hi, my name is Kevin and I was in charge of implementing the memory. Originally, the plan was to use the SRAM on the FPGA, but after talking to Peter, a solution involving arrays was instead considered. This design decision was considered due to the ease of implementation and the low amount of memory that would be required. The onboard SRAM contains 64 megabytes of memory, which is a lot considering that each reading from the sensor is only 8 bits. The memory module that I designed contains an array that can store 32 8-bit values. With that size, each square meter of a 4x8 meter room could be measured relatively quickly without too much hassle. If necessary, this capacity can be easily changed by simply changing the size of the array, but it is important to consider that if an array is too large, then the performance of the program may become affected. My memory module design contains only 5 ports. 2 separate ports are used for input and output data. One is for the address, while the other 2 pins are used for the clock and read-write pin. When the read-write pin is high, write mode is activated and the memory stores the input data to the specified address. Likewise, when read mode is activated, then the output data port outputs the data stored from the given address. After creating the module, I also had to implement the behavior for the record, reset, left shift, and right shift buttons. The record button simply writes the input data into memory. The reset button clears the selected reading, which is chosen using the left and right navigation buttons. Holding down the reset button is also supposed to clear all the readings. To keep track of how many readings there are, a register called global address is used to point to the next available address. Another register called selected address is controlled by the navigation buttons to change what data is to be cleared or outputted to the display.
Demonstration of our project, and as you can see, this is the 16x2 LCD. It's displaying the same result as the 7-segment LCD currently, and it's connected to a photoresistor. This is simply the photoresistor is connected to an 8.2 kilo ohm resistor in series, and it's connected to the Arduino, which is outputting an SPI signal to the FPGA. And we are using 4 buttons to record reset, and for left and right navigation. So now I'll show you an example. So I'm going to press the reset button. So this is the live reading. I'm going to shine a light on the photo resistor. It's going to resistance is going to decrease, as you can see. And then remove it. And now I will press a record. I'll press the record button. So you shine the light. It's hard to do one hand. Record. Record. And now I will press the left and right buttons to navigate through the record results, as you can see. Thank you for listening to our presentation.